So continuing on, this is number 19. The value of G for the gas phase reaction is, and notice it's G circle, so that means it's G at standard conditions, and a temperature of 300 Kelvin. What is G when the pressures are 0.5, 15, and 20 atmospheres? So looking on your equation sheet right here, you have to find the equation for G at non-standard conditions, and that's G equals G circle plus RT ln Q. So writing this equation down right here, G is equal to G circle, or G at standard conditions, plus RT ln of Q. And so we're told that G circle, or G at standard conditions, is negative 23.3. And notice that's kilojoules per mole. That's critical. Make sure you give it in kilojoules. And then R has to be the universal gas constant in kilojoules. So watch out for that. Make sure that you're taking your universal gas constant that is 8.31 joules per mole Kelvin and making sure that it's in kilojoules. So use this one right here. So 0.008314, and that's in kilojoules per mole times Kelvin. And then we multiply that times the temperature, which it said was 300 K. That's what they told us. And then that's times the natural log of Q. And Q, remember, is products divided by reactants to the power of the coefficients, just like K, except we're at non-standard. Well, we're not sure if we're at equilibrium conditions. And so my products are NH3 right here, which has a pressure of 0.5. And notice NH3 is going to have to be raised to the second power. And then the reactants are N2, which is 15 atmospheres, and that's going to be to the first power because it's just has a 1 in front of it. And then H2 is 20 atmospheres, and that's going to be to the third power. Now, do that on your calculator first, then go back and multiply it by 300, then go back and multiply it by 0.00831. Take that whole thing and add it to the negative 23.3, and then you get your G. And it turns out that G in this case then ends up equaling.
What's up, Benji?
I had the work up here. Here's our 0.831 and their natural log. Here's the products divided by reactants. So let's run the whole thing on a calculator so then you can see it. How about that? So 0.5 times 0.5, that'd be the top right here. And then we're going to divide that by 15, get an answer. And then we're going to divide that by 20 cubed, so 20 raised to the third power. So that gives us our number before we logarithm that. And so we need to take the natural log of that, so natural log of second answer. So that gives me what is circled right here. Then we're going to multiply that by 300, because that's our temperature. And then we're going to multiply that by 0.00831. That gives us this whole part right here. And now we add that number plus our negative 23.3, and we end up with a G at non-standard conditions of 55, negative 55.9. So it became more spontaneous, is what you could say, because it used to be negative 23, and now it's negative 55.9. And remember, the units are kilojoules on there. So that's number 19, a G at non-standard conditions problem. Number 20, the normal boiling point for a substance is 34.7. Its molar enthalpy of vaporization is 71 kilojoules per mole. Calculate the molar entropy of vaporization. So entropy changes associated with phase changes have this equation, S equals H divided by T. H is the molar entropy of vaporization or melting, and T is the boiling point expressed in absolute temperature, so it's got to be in kelvins. So we'll write this equation down. So S is equal to H divided by T, and our H right here is 71.8. And that's in kilojoules, so careful of your units there. And then we're going to divide it by our temperature, but the temperature has to be in kelvins, so we'll add 273 to this temperature right here of 34.7, and I believe we end up with 307.7 Kelvin. So we end up with kilojoules divided by Kelvin, and then those two numbers, let's do it on the calculator so then you can see it, 71.8 divided by 307.7, and I end up with 0.233, and that's kilojoules per Kelvin for my molar entropy, my S, and that's in kilojoules, and they'll probably want it in joules, so 3 to the right, so it'd be 233 joules per Kelvin. Okay, so that's numbers 19 and 20, and then from here on we go into some problems from chapter 16 and 17, which are acid-base problems. And so the conjugate acid, remember, is what is produced after the base has accepted its proton. So give one more H to this, and then we end up with H3PO4. So 21 is letter A. 22, a base is something that creates OH minuses in aqueous solution. And then in the Bronsted-Lowry definition, it not only creates OH minus in solution, but it is an H plus acceptor, is the Bronsted-Lowry definition of it. Number 23, which of the following represents a conjugate acid-base pair? So a conjugate acid-base pair would be one that has an acid with one more hydrogen and the base has one less hydrogen. And letter E is a good example of that, where we have H2O, and then once it gets rid of a hydrogen, then we have OH minus that remains. And then number 24, this one wouldn't be tested this year, but an acid is also defined as an electron pair donor, and this is known as the Lewis definition of acids and bases. In 2021, it won't be tested, but it could be tested in the future. So we'll pause there, and we'll come back with more acid-base problems next.